Week has gone well. Uh, who's Does anyone have any questions before we begin, or should we start off with Asmit? He has a paper to review.
Nothing from my side.
Okay. How about our other three?
Nothing from my side, sir.
Okay, that's good. Let's see. I'm trying to get the screen to work here. All right, Asmit, are you ready to present? Do you need to share your screen?
Yeah.
There we go. Okay.
Yes.
All right. So, all right, go ahead and present.
Today I'm going to present on my paper of choice, that is deep residual learning for image recognition, and the outcome of this paper, or the network that it finally gave as a result, is famously known as Resnet. And the main authors were Kai-Ming He, Jiang Hu, Xiaoqing Ren, Jian, and Jiansun. And this paper was presented at CVPR 2016. So CVPR is the most prestigious and honorable conference to present papers in the field of computer vision and pattern recognition. And this paper was really groundbreaking in a sense, and was presented in the 2016 edition of this conference. So I would start by giving it a kind of background in its timeline. So here's the ImageNet challenge. So ImageNet, it's basically a really large data set that was created by a lab in Stanford, a computer vision lab in Stanford, that contains a huge amount of human annotated photographs, and that belong to different classes, to precise around 1,000 object classes, and the training set is around 1.2 million in size, and the test set is around 100K in size. So basically, this and also corresponding to this data set, there was a challenge started known as ILSVRC, or ImageNet Large Scale Visual Recognition Challenge. So basically, every year, it's an annual challenge where every year the research groups, or like their algorithms, are tested upon this data set, and like they are priced according to their accuracy, like the minimum accuracy wins. Like this, the ImageNet challenge about around like 2012 or 13 became a matter of deepness of the nets. So basically, I would like to explain why actually this depth means something. So with more layers, so actually adding more layers to the network, you're actually increasing its capability of capturing more features, or more complex features which we can't see. So like, why did we actually move from shallow to deep? Was only shallow networks actually give great, or maybe even better results than deep learning, because we can understand the features. If you have a tabular data or a structured data, there's nothing better than normal shallow networks for that, because we know what features are what features are important, and like we can simply add them to our SVM or our random forest. We just know, because like we know what all is controlling it. But in case of some unstructured data, like an image, a video, or a sound, uh, like not sound, yeah, maybe sound, we don't know exactly like what we are actually searching for, because it's a vector, it's just an array of pixels, array of intensity of the pixels, and we have no idea about it. So like we leave it upon the a deep neural network. The main difference between deep networks and shallow is that deep can take out its own, like the neural nets can take out their own features which we don't know and train upon them. So more layers can cover more complex features, and equally it means the receptive field size increases because we are actually looking at more features and in more detail. And but there is a problem that training is difficult, and as we go deeper until this paper, as you can see, we have the IL SVRC 2014, which had 22 layers. The year before had 19 layers. Like we couldn't exceed 22 layers to get a good result, and suddenly there's a jump of around 130 layers to Resnet. So, like, what actually happened is really interesting to know, and it was because that it's not that we suddenly had a jump in computational power that caused such an increase in the amount of layers, but there was something more important in play. So, about the author, it's Simon He, and at the time of the this paper, he was working with Microsoft, and currently he's a research scientist at Facebook, and his areas of interests are computer vision and deep learning, and he has great works in these areas. So, introduction. ResNet can be defined as a clean framework for training very deep nets, and it's not simple, but it's relatively simple to its predecessor, the Google net, like which was humongous and really difficult to understand. And it's a state of the art for image classification, object detection, and semantic segmentation. Actually, the library we are going to use in our Basic area project, that's Deep Lab, it's actually built upon a ResNet only. Like it's a pipeline of many other models, but the main contributor is ResNet. And here at the bottom, you can see the results. How groundbreaking it was. Like we had for the first time cross 100 layers to 150 layers, and we had 16% better than the second accuracy. Like that's a lot of difference, 16%, 27%. And like similarly to ImageNet, we have a Coco challenge, and they also had 11%, 12% increase. And regarding let's start with the evolution of depth. So that's the same thing. We have AlexNet at 8 layers, then we had 2014 VGG 19 layers, and then GoogleNet 22 layers. That was the best performing till then. And then ResNet came with like 152 layers straight. Then yeah, so till now it seems like just adding layers maybe increases our accuracy, but it's simply not the case, and it's there's much more at play. What really happens? So, like, what if we just stack layers? What if we just increase our layers from 20 to 56 in a plain CNN? Like, if we increase from 20 to 56, even the training error is decreasing. Like, this is really shocking or not easily understandable, because like it's by simple logic we would think that if you are increasing the capability of the model uh, to capture new features, it should at least get better results in the training part. And because until then, before the paper, people were actually didn't know like what was the cause of this. Like what caused that training, even the training error is less than with less layers. And then there were the main two things that could have been at play before that would have been that maybe the model was overfitting, but that's also clearly not the case, because it's simply ruled out because the training error is increasing instead of decreasing. So if we are actually overfitting a model, at least the training error increases. For example, if you are training a model on a data set of cats, so if you are training on cats and we just increase our layers, it may be possible that the neural network starts seeing features that are not important. Something if some amount of cats have bells on their neck, so the model will start capturing the bells, and if we get a dog which has a bell for some reason in the test set, it will classify it as a cat, like just for example. So in that case, at least the training error should have increased, so it's not overfitting. And then there's another thing known as diminishing gradient problem. That's that like the differential of the grade. Like if you're using something like an SGB or like the gradient descent as a as the main logic, then if you have so many layers, it may be possible that your gradient is like getting decreased so much across the layers because it's every time taking the differential, and the gradient is normalized between -1 to 1, that it may become so minuscule that like it will have no effect. But it was also controlled, and it was seen that that is also not the case. So like people were really curious to know what actually was in place. So this paper was also really important in telling like what was the actual reason for this. So what actually came out was that the main problem is the optimization problem. The model is not, like with so many layers, the model is not able to learn, like take out like the main like actual reason. If you go mathematical, it's still not there, but it's in hypothesis that the main cause is that there is an optimization problem. The model is the main optimization function is not able to learn properly across so many layers. So ResNet actually came with a different approach to this by changing the entire, not the entire architecture, but the architecture in some way. So it solves the degradation problem. The degradation problem is the problem of decreasing accuracy in the training itself. Then it's also a faster training of deep networks as compared to the other algorithms. Like I don't know the exact reason, but like it has a much lesser time complexity, and also with so many layers, it doesn't actually increase the parameters of a feature. Like it's not actually increasing a lot in terms of parameters, and it's obviously has high accuracy. Okay, so the common method would have been in terms of increasing layer, we would have a weight layer, we would have an input, the activation function, which can be really all sigmoid or anything, and then we'll have an output h of x, which is a mapping function from input to output. So normally we will train on this h of x. So what the main problem was that with so many layers, this was not able to train properly, and it was messing up. So the groundbreaking thing was the coming up of these residual functions, f of x. Like we'll be training on this new kind of function, f of x, which is a same thing. Like it's the, if you take h of x, your final output function, it is just the h of x minus x. So we'll be training on f of x, and h of x can be recovered by simply adding x. So like it was hypothesized that this should actually solve the optimization problem, and it was easier to train on this. Like, and in reality also it came out to be true that it was easier to train on f of x instead of h of x. Like I don't know the exact reason for that, but it was hypothesized, and like I guess if there's a proof, but it was easier to train on f of x as compared to h of x, and that caused the optimization problem to go away. And for example, like for simple example, for in an ideal case, we have a simple points, like data is simply a line, data is forming a line. So in that case, h of x should simply give x. Like if it's y is equal to x, the h of x will simply train on x. In that case, like we can think in that way that h of x would have to train on a linear example, while simply taking h of x, while f of x will have to be 0. So it is much easier to feed 0, like train or give it f of x 0 instead of training h of x on x. And these shortcuts, like the loop you see, it's simply passing x, which is identity, so it's also not computationally very expensive. And that's the main thing. We are passing x, and the h of x can be retrieved by fx plus x. Here at the end, we can apply an activation function. So the contributions of this paper were it showed that the residual learning uses optimization. From like normal learning, we came to residual learning. It was using optimization. It tackles the problem of degradation. It was decreasing error rates of deeper networks, and it achieved 3.57% error rate in ImageNet, which was much better than its predecessor, and it's actually greater than the human error. Like human error is around 95%. Human error is around 5%, so it's actually performed first time better than the humans in classifying these images. Real world applications involve image recognition, image detection, localization, segmentation tasks, and like these are the competitions that's aced, and it will also boost industries like medical image analysis, space and satellite imaging, robot vision. So this was the testing, or basically the experiment, which actually shows that now increasing layer is actually decreasing the error rate. So in plain network for training, we'll have 27.94 training error and 27.88, which has decreased, and then with 34 layers, the plain net is showing 28.54, while ResNet is 25.03. So that's 3% decrease in error. So like after this, actually increasing layers properly with proper architecture and making use of residual function actually helped in decreasing the error rate. The findings of this paper were mainly the degradation problem, the cause of the degradation problem, that it is not due to overfitting but due to difficulty in optimization, and that h of x minus x is easier to optimize than h of x. No, h of x minus x is f of x. And residual learning helps train better networks, deeper networks, and these are the like all the things that perform really well in like first time. I just mentioned that first time to go over 100 layers and 16% better than the second. Like all of them are like huge increase in terms of accuracy. Thank you. And any questions?
Well, thank you for presenting. That's a very interesting paper. It gets us back to a question someone asked a couple weeks ago, which is, what is the relevance of adding more and more layers to a network? And so that answered the question pretty well, I think. There's a question in the chat from Ujwal. This paper solved one of the problems, like tiger is still detected as cat in many models. So to have like a visual, like false positive, or where you're identifying something else, or you're identifying the thing, but yeah.
So I guess I can, like, because it is now correctly classifying it as a type instead of practice, because now actually we are getting more features and not while maintaining our accuracy. So like we have more layers, that means more features, and we can correctly classify a type as a type instead of a cat.
Okay. Anyone have any other questions?
Hi Asmit, I don't have a question. I like to add just two things. The first is that I just googled images challenge and it is currently held on Kaggle for the last 2-3 years. It is currently taught by some KLE Tech Hubli, which is some small institute in India. That's great. I mean, Google and Facebook research labs, IBM research labs also participate in these challenges. That's great. And the second thing I wanted to ask was that this was the first like deep network that they could actually train well. So by just modifying the architecture small bit, like the adding instead of h of x training h of x minus x, they could train such deep neural network.
Yeah, it was just like minute change in the architecture that caused such increase, like that caused to train such deep models. Like the last model had only 20 layers, so now we had 152 layers. The main.
That's great.
Any other questions? So I had a question about the layer. So you showed a graph where they were adding layers, where they showed like where they had like 20 layers and 50 some odd layers, and then they showed the error rate, and they showed that it actually increases, which is of course motivates the rest of the work. But then what about, why is it exactly that it doesn't guarantee you'll get better accuracy? It's about, let's see.
Yeah, because it was people thought that it was either overfitting or the problem of vanishing gradients, but like then during this paper, it was hypothesized that it was actually due to a problem in optimization. So like if you're going across the layers, the h of x, like the network is not able to properly train upon that function with the provided time. So So we actually needed a change in the architecture instead of just like changing the amount of layers. And also at this point, it was thought that maybe it's not possible to get better results with more layers. But so they thought that if we just add more layers that do not do anything and they're redundant, so basically that should at least give us the same accuracy, if not better. So that was also not happening. So then the cause was that it was the optimization problem that was actually causing it.
So optimization means underfitting, like in some
Not
sense.
underfit.
Like you can say they couldn't properly train the whole network,
Yeah,
such deep networks.
yeah. It was
That is why
like
it was not performing.
yeah, it had so many features to extract. So like some features were easily available to train. In some sense, like it was easy to fit weights upon some features, but some features were not easily to train their weights upon. So like it was causing overall like decrease in accuracy because it was not properly training, like in some sense. Like I don't know about the deep maths, but like it was mentioned that it was not properly training, and overall uh, it was an optimization problem.
Okay. Yeah. We have a lot of texts from Ojwell. So he commented, adding new layers doesn't guarantee that you will get better accuracy. It's about using residuals from the previous layer. And then the way they used residual features again in the neural networks is something which is groundbreaking. And then he commented on optimization. Optimization means you are optimizing parameters to make your model more detailed, and then covering more and more features in general. So, yeah, I mean, that's the impression I got, that they had a lot of features and that they were able to get more resolution, but there is that caveat where you have more error as well as you keep adding layers. So that's something you have to overcome. And then they showed that you can overcome them using their methods. So I think that's good. I think that's a very good paper. Thank you, everyone, for presenting your papers. Paras, actually, if you want to present a paper, you're welcome to do so. If you want to do it, just send me a paper selection. You can go to the archive, or you can go anywhere to any of the conference proceedings, find a paper, and then present it one week, and it'll be like in the same format, 15 to 20 minutes. So, if you want to do it, that's you're welcome to do it. So,
So I will look into it.
okay, yeah. So next thing we'll do is we'll go to the boards. So the first board we have here is, we'll go to Vinay's board first. Let me put his repo in the chat. And then if we go to that repo, we go to the projects tab. Then we go to Summer of Code projects. And so I think a lot of the stuff we have a lot of things in done, and we'll skip that, and we'll go to what's in progress. So number 23, implemented custom layer in Keras from TensorFlow.
Yeah, I basically want to. I did some work this week, and I want to present my screen to show the outputs. Is that okay?
Sure, yeah, go ahead.
Yeah, please. Please give me a second.
Okay.
Alright, can everyone see my screen now?
Yes.
Yeah, okay, so if we go to this issue right here, the issue was because initially I implemented the model with TensorFlow with Keras, which came from TensorFlow, which uses TensorFlow backend. And for that purpose, I needed to use some custom layer. But then I had a limitation with using custom layers and importing those models into deep learning for J. So basically, I had to re-implement the whole model in pure TensorFlow, where this use of custom layers can be avoided. So this is the notebook. This is the model that I'm training on Kaggle. Yeah. So
Okay.
basically, this week I had to try out different versions of the model, because even in low-level TensorFlow there are different modules. Like for suppose, if you take convolution layers from tf.nn, like this is the pretty lowest level of API which TensorFlow provides, and you build the model. And there's also other way of using these convolution layers, which is tf.layers. Basically, these two have the same goal, to extract features and to make sense out of what is going through the model. But the way they are implemented is different. So if we implement a model with entirely with tf.nn and df.layers, we will be getting slightly different outputs. So I had to experiment with different versions of the model, and I like to show some outputs from which I've got. Also, in the feedback that I've got from Sir Bradley Sir, is
Yeah.
that I need to concentrate on that semantic aspect of the problem, right?
Yeah. I mean, we haven't really gotten there yet, but I think that leads into some of the stuff in the second and third phase. But yeah, that would be good if we could, deal with that more explicitly, maybe in the meetings and in keeping an eye towards that in the work.
Yeah, I actually thought about that, and I thought the original loss function that they mentioned in the paper, the soft cut loss function, that is actually important for this semantic approach, instead of that ordinary loss function that we've used earlier. So I had to go back to that a soft cut loss function, and I've implemented here. And also there are two versions of software normalized loss function that I've implemented. So basically, I had to try out different combinations of these models, and loss functions, and also parameters included. Basically, that I did this week.
Okay.
So I want to show some outputs that I've got here. So there are three versions of the models that I've created. One is this model that you're seeing right now. This is entirely created with tf.nn, like the lowest level of API that TensorFlow is providing. And for that, and with that, I've gotten outputs looking like this. Here you can see each of this pixel is getting a value, is getting a class, whether it's based on whether it's a background or it's an edge. So this is how it came, using the model, using the first version of the model, like using tf.nn. And after that, uh, I used tf.layers actually, after that, to see how the result varies, or does it even vary or not. So for that, I got this output. Here, this is much better, that you can see. Here the edges got highlighted, and all the noise has been removed from this image. So far, this is the best output that I could get, where the edges are highlighted,
Okay.
and the background is nullified. And also there's another version of model that I've tried out. Before going to that, I want to tell the basic difference between tf.nn and df.layers. In tf.nn, we need to specify the weights and biases for each of our convolution layer. Like we need, like in here, uh, I had to define the weights and biases for each of the convolutional layer or batch normalization layers that I've included in my model. That is the case for tf.nn. But for tf.layers, all of these weights and biases, I don't have to specify them. TensorFlow by default gives it some values, and by that it comes. By that the training happens. So the third version of the model that I've tried is that, uh, I've used the layers from the convolutional. I've used the convolutional layers from tf.layers, and for the batch normalization, I had to use NN, like the batch normalization layers from tf.nn, because on the internet I found out that these mean and variances that the batch normalization supervises is most important. So based for that model, I got this output. This is pretty noisy actually, but the idea is good. See here, you can see the cell background being given green color,
Yeah.
and the cell is being red color, and the background is given blue color here.
Yeah.
And there are basically so many parameters that have been included in this model, like the dropout rate, number of epochs, and also for the loss function. There are some parameters which affect the output: the radius parameter, the intensity of the pixels parameter, and the distance to from which the cut loss happens. That is this sigma std. So this week I had to try out different combinations, like increasing the radius or decreasing the intensity at one point, and see how the model outputs. So basically, that I did all that this week. I had to put a lot more hours, because each of this training took me around 1 hour each. So I was able to do that much this week. And these are some other outputs which I've gotten with different set of parameters and model combinations. I'm just going through them.
Yeah.
So I want to know from you, sir, like how like which one looks good, like from which output looks good, as like close to what is expected.
Right. So I guess like the one like if you had some that basically are multicolor maps, that's something you can go and decompose by counting the number of pixels that are of a certain color within a certain boundary. I mean, basically that's what we want, kind of a map that shows the boundaries pretty clearly and then shows the interior of the cell. So you have like maybe something like the image on the left is better for the purposes of what we're trying to do than the image on the
Okay.
right. But the image on the right also has, I think the boundary might be a little bit more defined in that one too on the left hand side. Um,
Yes.
it's going to be a little bit tricky to get like. I guess the next step for that would be to kind of like maybe see what kind of statistics you can get out of the image. Like if you were to then like count like find out where the boundaries are, what's inside the boundaries. So if you were doing like um, a simpler type of segmentation where you took where you just segmented the thing um, into areas, defined areas, using either the boundaries or the interior part. Actually, the blue part here would be the thing you'd be interested in, and then you'd segment the image based on like what's inside the blue areas. So you might have a bunch of different cells that you'd segment out of this image on the right, where it would give you like a size of the feature, and then like maybe like the centroid of that feature, and then that's kind of the thing, the kind of the goal here for the next step. So if you want to do that, if you want to try to segment these images more simply just by using like you know just like some sort of centroid method, then you can actually get like numbers where you have like the location of different cells or blobs and their area, and that might be
Yeah,
informative,
yeah.
and see how much you can get out of that makes sense. I mean, I can work with you on that. I mean, and then it would just be test them and see which one looks, which ones look better, because it's hard to say which ones actually look better just by looking at them. The criterion should be something quantitative, but I don't know what it's gonna do. I mean, I don't know what it's actually gonna pull out of the images. You know what I mean? Like,
Yes, yes. Basically, I also got this idea of doing K after this model has outputted this image. Basically, if we do some other unsupervised segmentation basically clustering algorithm like a KNN algorithm. Sorry, K means clustering algorithm. Basically, that if we do something like that, that actually depends on centroids, and I think maybe we could get some useful the output that that you're talking about, like the cell boundary, the cell having a different color, and the boundaries having different color, and the background having different color. So after that thought, then I had a limitation in mind, because after the model after the model outputs this, the k-means clustering will be a post processing to this image, right? So after we need to import this results into image which is written in Java. So it's basically very easy to do k-means clustering in Python, and also I don't know how well it will replicate if we like how close it comes if we replicate the same in Java. So basically that I had that in mind.
yeah,
But I'm willing to try out. That looks like that sounds like a promising idea, and yeah, I'll let you know the results after trying out k-means clustering on this, and I'll see if I can replicate the same also with Java, so that I'll not have to deal with all the hassle between the differences.
yeah, yeah. I mean, but so what we're looking for is just like a down and dirty metric for which one is better at like picking out the proper things out of this image. So basically what you've done is you've taken the image and you've kind of defined a skeleton, and then that skeleton, now we're going to take it apart and we're going to see which one's more accurate, or which skeletons are more accurate for the purposes of the next step. I mean, the reason I was so vague about like the algorithm is because, of course, there are a number of algorithms you could use. I think k-means clustering is probably good. um, it's something that uses a good criterion for finding the edges and defining the areas. And then if you have a feature like the background, it's pretty easy to identify it. You can just simply say, it's the largest part, and we know if the feature's over maybe like 6,000 pixels, we know we can throw it out because it's obviously wrong. So we know kind of the size scale, and then so we know the size scale of it. Oh, there's some feedback on this. Your volume is too high on your.
No.
Oh,
Oh,
okay.
sorry. Okay, okay. Sorry, sorry.
Okay.
Oh,
Yeah, I think it kind of, yeah. Okay, so yeah, I mean that, and then yeah, and then there are other tricks like you can invert the image, or do some other basic tricks to sort of augment the skeleton here. So I mean, depending on how the k-means algorithm's picking up on the edges, you can play around. You can reduce the number of colors to 2 or something like that, just to give just to give it a little bit more of an edge in terms of you know uh, providing it with the good input. So I that looks good. I like that you tried a bunch of different options on that, and you did talk to me earlier this week about having to re-implement everything. So let's see. This number 23, I think, is done in terms of the issues on the board. And then use deep learning for J, number 8. I think that's also done because you've pretty much mastered that. So then we need to have, I think, a new issue here. Maybe test output images. with k-means clustering. And then that'll just be like what you were just describing to me. And then we can put assign that one. And then, you can just we can work together on Slack on that. You can just send me like results if you find something really exciting or whatever.
Yeah, sure, yeah.
Yeah. So then are there any other issues for that, or do you think that's good for now?
We can address the to-do ones now. Can we address?
Yeah. So the build a plugin and conclusion of plugin development, that's kind of for later. Limitation of deep learning for J number 21, is that still kind of in play?
No, I think it's done because now that I've re-implemented it completely in TensorFlow, there's no need for any custom layers that will stop me from that. So for now, I think it's done. Yeah.
Okay. Right. So then that brings us to do and begin work on semi-supervised approach number 17.
That's a phase 2. Yeah.
Okay. So that's it. Still to do.
Yeah.
Okay. Implement soft cut normalization loss.
Yeah, I've done that. I've actually implemented 2 versions of it, so that's pretty much okay. That I think that can be put in done.
Okay. Segmenting bright field images. That's
for phase 3, right?
Yeah, that's to do.
Yeah.
And then DevoWorm and neuroinformatics outreach. That's still kind of to do.
Yeah.
Okay. So any other issues you want to put up on the board, or is that we can just
no? I think this will be fine. Now I'll have to test out with k-means clustering or similar means clustering.
Okay.
Algorithm. Yeah.
Okay. Well, that's good. Keep me in the loop on how your progress goes. Did you ever put the extra memory in your machine?
Yeah, I've added last week. Basically, I had to go to out of town for that. I've added a other 4 GB RAM card to my system. Now it's 8 GB.
Well, good. Yeah. You finding it easier to do stuff with?
Yeah, basically, the problem I've had with that 4 GB system is that even after I've trained the models in Kaggle and if I've downloaded the model, I'm unable to run that. Basically, because this is it has about 18 convolution layers and some heavy training. So my memory was not sufficient to load that model and pass a test image to that model so that I'll get a prediction. So basically, for that purpose, I needed some RAM, and now I think it's pretty good.
Okay, that sounds good.
Yeah.
So, all right, now we turn to Paras, Asmit, and Ujwal. So, are you guys? How are you doing? Do you have any issues that you want to discuss before we go to the board, or?
So actually, we have made a very good progress this week, and we have almost labeled around 80 images, and we have started producing results. We will try to show you in the next weekly meeting, like what we have got.
Okay.
So we are in almost final stage of getting all the images segmented and in an unsupervised way.
Oh, that sounds good. Yeah. Yeah, you'd been talking about how you were kind of like going through that and trying to get it established. So I look forward to that. But why don't we go quickly to the board? So I put the link to the repository in the chat. And if you follow that and you go to that repo and you go to the projects tab, you will see the digital basilaria board. And then we now have quite a few things in done, which is good. We have quite a few things in progress, and that's where we'll start. Number 17 is I'm still working on this, adding information about the biology of basilaria. We had a couple of exchanges this last week on things, so I'll catch up on that. Description of neural networks. approach for biologists, number 31. I think this was the point of this was to write a little description of neural networks that was very simple.
Yes, sir, I have started documenting the neural networks and I'm in the final stages and I think I will share it by Sunday itself.
Okay, good. And then 29 template methods. So in Slack, I sent a copy of the paper that we were looking for, Sabunku et al. I don't know if I sent it in a private chat or in the channel, but it should be in Slack, accessible to you guys. It's basically the paper that they published on. I think it was on the just a very basic overview of measurement techniques that they were using, and so if you go to the methods of that paper, you'll see some of it. We'll go through that in more detail, I think, later on. Maybe not this week, but just so you can look it over and get yourself familiarized with it. And then,
Okay, sir.
yeah, and then review Subunku. That's number 30. That's just what I was talking about. Documentation and procedure, number 36. That's actually where we're actually documenting what we're doing on the training. So we're creating a training set and then make sure that you're documenting everything so that we can go back and we're going to turn that into like a methods section. So we want to have good documentation, and that's just a reminder. Labeling data set, number 35. So we're coming along on that. Is that our...
So we have labeled the dataset for the folder 1 and 2 and it is a thing like it will if we will start trying producing results, but if we think that it is not so detailed, so we will train more labeled dataset. So I think it should be there in.
Okay, so we're basically still in progress on that. And then model evaluation, that's going to come a little bit later. And then Kaggle kernels, I guess that's... So did you ever use that, or was that something you passed on? I can't remember.
So actually we tried to use cable kernels, but we are not so familiar with it. So what we have done now is like we are three team members and we all of have almost one or two PCs at our home. So we have started parallelly training all the models so that the things will speed up a little bit.
Okay. Well, I'll put Kaggle kernels and done, just, and then so we have that. Okay, so in progress is done. Now let's go to the to-do list. So welcome to Paras, and we'll talk about a presentation, so we'll put that in progress. And then you can send me the paper. Model features within and between frames, number 28. I think that's for a little bit later on. Mathematical model development. Again, that's actually something I have been... I got some stuff from Thomas, and I haven't really... I've reviewed it a little bit, but I don't know. I might pass it on to you later. But is there any more thought? If people given any more thought to mathematical model development, or is that something that is down the line a bit?
So we have read about something like how we can evaluate these models, and the one thing is like we can mark 2 points on the edges of basilaria, and then we can find the axis of rotation of basilaria if it is moving or not. And we can also find like we have points on XML files, so how much it is displaced in different XML files of different frames, and we can evaluate on them like we have done something right that we are trying to do it, but we don't know whether it works or not.
Okay. Well, I mean, that'll probably be like for later. We'll just we'll be able to actually test it later. But okay, so I mean, that sounds good that you've at least been thinking about it. We'll address this more in coming weeks, but I just wanted to see where you. Maybe we'll put that in progress since we're kind of already thinking about it, and we're not quite there, but we'll get there. Then create video resources for bacillary biology, number 21. That's still kind of out there in the coming weeks. And then define features within and between frames. That's going to require 28. So that's going to be left for later. So before we go, are there any issues that you can think of in the next week that you want to put on the board?
So I don't think so. Like we have any issues to put on board. We are trying to get results as soon as possible and try to show you by the next meeting.
Okay. Actually, why don't I just make that as an in progress issue? Okay. And then we'll just turn that into an issue. And I'll just assign it to all of you. Just so we can revisit it when you present. Okay. All right, I think that's good. Thank you for the updates. It sounds like you guys are making progress. Next week, we will have a presentation from the Digital Bacillary trio on their progress. And that's for all. I think that's all for now. Again, you can Slack me during the week or email me. And thanks to everyone for your efforts. And talk to you next week.
Okay, thank you, sir.
Yeah, thank you. Okay, anything else?
Yeah. Thanks. I hope everyone has a great weekend.
Yeah, thanks. Have a good weekend.